Okay, wonderful. Now that you know the basic building blocks of deep neural networks, together with your knowledge about general machine learning systems, you have all the tools you need to basically build deep convolutional neural feature extractors and models around them to do classification tasks. Now, people have been doing this since several decades, and in this section, we'll talk a little bit about popular network architectures and also a little bit about the history, because this can be quite informative how and interesting also how certain things changed over time. So let's just dive right into it. This is the famous LeNet 5, and this was developed by Jan LeCun directly and his team in 1995. So firstly, it's important to appreciate the historical context. Back in the 90s, the field of deep learning was really nowhere near as advanced as it is today. And creating a neural network was a significant engineering challenge. So building LeNet 5 was a monumental effort that likely took between 3 to 6 months to implement, including all the tooling. There were no frameworks for deep learning, nothing like by PyTorch. So let's look a little bit at the architecture here. And the architecture, so LeNet was initially really designed for low resolution black and white image recognition, specifically for digital handwritten digits. The input to the network is basically just a 32 by 32 pixel grayscale image, like here. The first step is a convolutional layer that transforms the input into 6 feature maps, each of the size 28 by 28, and that is followed by average pooling. An average pooling layer reduces the dimensionality further to 14 by 14, but still remains 6 channels. A second convolutional layer further reduces the feature maps to size 10 by 10, but increases the number of channels to 16. And another one, another round of average pooling halves the dimension again, leaving us with here 5 by 5 feature maps with 16 channels. The architecture employs fully connected layers at the end, and the first is 120 units, followed by another with 84 units, and the last layer is quite interesting. It uses a Gaussian radial basis function to map these features into 10 classes. Given the technology and resources available at the time, LeNet 5 was a significant step forward in the field and laid really the groundwork for future CNN architectures. It's really crucial to recognize this contribution, to show how far we have come and how these early networks really influenced today far more complex architectures. Now, why was this a big deal in 1995? Well, the answer just lies in the immediate application potential of the technology. The times were different back then. At the time, AT&T had an ongoing project focusing on handwritten digit recognition. And this was not just an academic exercise. There was real commercial interest and immediate need. Specifically with banks and postal services were seeking ways to automate their operations. Imagine the postal office. Every day they would receive thousands of letters with handwritten postal codes that needed to be sorted and processed manually. And similarly, banks had to deal with handwritten checks, including handwritten amounts that needed to be read and processed very accurately, right? And automating these operations would really save time and also reduce potentially human error, but it requires a level of technology that could reliably perform that handwriting recognition. So not only did they need to recognize the characters, but they also had to locate them within a larger document, a form of object recognition. You can't predict what a digit is until you know where it's located on the page or on the check. That's where Learnet came in. Its pioneering architecture really demonstrated that CNNs could reliably perform both tasks, object localization and recognition on low-resolution black and white images. It was the solution to a problem that had immediate practical applications, making it a really significant milestone, not just in the field of machine learning, but also for all sorts of commercial technologies. So MNIST was created specifically in this context for handwritten digit recognition. This is the data set Learnet was trained on. It's a curated collection of centered and scaled images, making it easier for models to learn the necessary features, really. The dataset is divided into 50,000 images for training and an additional 10,000 images for testing. Each image is at a resolution of 32 by 32 originally, then they started to resort to 28 by 28 pixels, which keeps the computational requirements quite reasonable without sacrificing too much detail for these sort of digits. Now you might wonder why there are exactly 10 classes in MNIST. Well, the answer is straightforward. There are 10 digits, 0 to 9, that we commonly use, right? And it's worth noting that these aren't just any digits. They are realistic digits obtained from real-world examples like letters. So somebody sat down and really scanned all of these and then prepared this data set. Very likely somebody from Jan LeCun's team. And these digits have been segmented also properly to ensure that they are good representations for the task of handwritten digit recognition. So to date, MNIST data serves as both a benchmark and real-world application resource. And since it really first was released, it continues to be a staple in the machine learning community. Now, this is the original demo from 1995. Let's see if it plays. This was truly amazing at the time, where the characters have been correctly identified. Also note that it can recognize when it doesn't know the answer, when in between characters, it tells you it doesn't really know, which is likely derived from the output layer, a separate class. You can model this in various ways. Now, the problem with Learnet is that these fully connected layers here are very expensive and basically prevent this to scale to problems like images or problems defined by large image data sets like ImageNet. And ImageNet has perhaps 1,000 different classes, and the fully connected layers become really a computational bottleneck for many, many classes. So while they are straightforward and effective for smaller problems, they can really complicate the architecture when scaling up. So the final layers here really become a dominant factor in network design. And that's why alternative strategies were needed to handle the computational expenses for large scales. And while this is how you would implement Learnet in PyTorch nowadays, I'm pretty sure this was one of the main reasons PyTorch was created, because that was definitely not as easy as here for Jan LeCun and his team in 95. So it's a good opportunity to have a look a little bit in what you need to implement in the net. So what you have is a module you need to define for your network. You initialize your layers, you define them what they are supposed to be, convolution layers, linear layers, and so on from PyTorch. And you define a forward pass. Here in this case, there's another flattening function, but the forward pass is the most important one. We define how the network is connected and the tensors fit to each other. The nice thing is that AutoDiff in PyTorch does the rest for you. If all of these functions are in modules from PyTorch, then even if not, sometimes it works, but if they are defined like this, you get the gradient for backpropagation directly. So, but this is how learned looks like nowadays in PyTorch. Now, next breakthrough was basically in 2012 when AlexNet was introduced and really outperformed all the other approaches for the ongoing computer vision ImageNet challenge at that time. So it really completed the ImageNet classification task and drastically outperformed all of the other non-deep learning heuristic feature extraction models that were there at the time. So this architecture probably really kickstarted the widespread adoption and research into CNNs. Structurally, AlexNet basically is a learned, but with a few key differences. So first of all, it has more layers, 5 convolutional layers and 3 fully connected layers here at the back. The input images in ImageNet are 224 by 224 pixels with 3 color channels each. And unlike Learned, which handled a much smaller grayscale images, AlexNet used also 11 by 11 filters with a stride of 4, though later research has actually shown that smaller filters can be more effective than them. AlexNet used quite large strided filters in the initial layers. And the fully connected layers at the end were size 4096, and the final layer connected to the 1000 classes in ImageNet through a softmax activation. Now, if you ever looked at an AlexNet diagram like that, you might notice it's actually split here into 2 columns or streams. So one goes here, one goes here. This one is just south. It's the same as the bottom, but it's cut off in the original paper as well. This figure is from the original paper. And the only reason for that is that the network was trained on GTX 580 GPUs, which each of them only had 3 gigabytes of memory. And to fit the model, the architecture was divided actually between 2 GPUs, and each handled half of the neurons or half of the feature maps. And in layers like Con1 and Con2, 4, and 5 feature maps from the same GPU were used for connections. However, in the layers Conf3, 1, 2, 3, and fully connected 6 and 7, both GPUs communicated here to give neurons a full view of the preceding layer. And this kind of parallel processing is actually far easier today, thanks to features in modern frameworks like PyTorch Data Parallel, where you can do this exchange kind of automatically. So AlexNet wouldn't be implemented nowadays like this. You would just use the entire size on one stream and then have basically a bigger LearnNet doing this task. So ImageNet is an interesting also benchmark data set, which led to AlexNet image classification breakthrough. ImageNet was released in 2010 and was considered a massive data set at the time. It contained a whopping 1.2 million examples distributed across 1,000 different classes. To give you some context, compare this to MNIST, which only had 60,000 samples and 10 classes. And not only did the quality of data change, but also the complexity. So ImageNet featured images with dimensions ranging from 469 by 384 pixels. This is a significant jump from MNIST 28 by 28 pixels. So ImageNet images were also in full color, represented by 3 channels, red, green, and blue. And this was a departure from the grayscale images that networks like Learned or in general computer vision at the time were designed to handle. And the increase in both the volume and complexity of the data made ImageNet really a very challenging task, but also one that showcased the capabilities of models like AlexNet. And this data set and its challenges really pushed the boundary of what was possible in image classification at the time. And without these sort of data sets, there wouldn't be a deep learning paradigm shift have happened in 2012. So before these two milestones, the common practice in computer vision was to manually engineer features and use, for example, a support vector machine for classification. And AlexNet really revolutionized this approach by learning features automatically and using a softmax function for the classification. However, AlexNet was more than just a scaled-up version of LearnNet to some degree. One significant innovation was really the introduction of dropout regularization during training, which is not quite obvious in the feature in the network diagram. Dropout really allowed for much deeper networks by introducing regularization not just at the input layer, but through multiple layers of the network. You just randomly deactivate certain neurons during training, which is a great way to regularize and to make the training task harder for the network. And this made it possible to really control the complexity of the model more efficiently. Another important change was the use of ReLUs as activation functions. So ReLUs really helped to mitigate the vanishing gradient problem earlier LearnNet versions were experiencing. And this enabled training of really deeper networks more efficiently. And max pooling was another change that replaced average pooling in AlexNet. So LearnNet used average pooling, AlexNet used max pooling. And this made the learned features more shift invariant, which is important for object recognition, as was the main task in ImageNet. And really, to secure their win, the AlexNet team employed heavy data augmentation as well. It's just something we'll also talk about, but techniques like cropping, shifting, and rotation along with model ensembling made a really, really powerful class predictor here. So that is one of probably the last decade's largest paradigm shift in computer science. But still, nowadays, probably very few people would use AlexNet. So it's just a summary of what I just said. AlexNet uses larger kernels and larger images and uses max pooling instead of average pooling. You don't need to memorize this by heart. It's just that people were experimenting with this and that, had some hypotheses, and the larger kernels here purely rooted in the fact that the input is larger. So this was the idea, okay, we need more information. But later it turned out that this is actually not necessary in small convolutions, and more of them can do equally well. So your more technical key changes that AlexNet used, the pool size was also increased and max pooling was adopted, as I said already. So it's meant to capture more complex and varied features from the images, and the number of output channels, of course, was also increased significantly because there were much more classes to be identified in ImageNet than in MNIST. Okay, so from terms of complexity, compared to LearnNet 5, AlexNet is substantially more complex. So it's about 250 times more computationally expensive than LearnNet 5. However, in terms of the number of parameters, it's only about 10 times larger than LearnNet 5, so that's not too bad. This brings us to an interesting point about the trade-off between computation and memory. AlexNet is notorious for its high memory usage, particularly when it was first introduced. It's interesting to note how this trade-off has actually evolved over the years. Today, with advancement in hardware, the ratio probably skew more towards computation rather than memory, but with less computational power, you would use more memory. And modern GPUs can really handle complex calculations much more efficiently, which allows them to really run computationally intensive models. So AlexNet made it into popular culture, or the deep learning hype. if you remember this this episode from season 4 Silicon Valley is what actually the research in this domain did to people and even made it into comedy. So yes, the clip is meant to be a joke, but I think it really puts it to a point what people were expecting at that time neural networks could do.
It's ready.
Please, God.
What will you say if I told you there is an app on the market?
We're past that part. Just demo it.
Okay. Let's start with a hot dog.
Holy shit! It works!
Oh, motherfuck!
Huzzah!
Jin Yang, my beautiful little Asiatic friend, I'm going to buy you the palapa of your life. We will have 12 posts, braided palm leaves. You'll never feel exposed again.
I'm gonna be rich. Fuck you, Guilfoyle. Do pizza.
Let's do pizza.
Yeah.
Okay. Pizza.
Not hot dog?
Wait, what the fuck?
Huh?
That's it? It only does hot dogs?
No, and a not hot dog.
So this captured the imagination and excitement around what neural networks might potentially be able to do.
It's ready.
So an advancement on this side was so this is just how you would implement AlexNet. AlexNet is similarly simple to implement now. You would just not split the network up anymore, but have the whole thing in one go and then implement your forward pass by adding together all your activations and convolutional layers. Now, a further advancement was the VGG network, named after the VGG group in the UK. So the way VGG works, and it's still a big backbone of a lot of feature extractors, is has been developed by the University of Oxford Visual Geometry Group, and it took inspiration from AlexNet. It said bigger is better and decided to take it a step further. And in doing so, they created an architecture that has been widely used and adopted in various computer vision tasks. So what did they do actually in detail? So one way to make a network larger is to add more dense layers, of course, but this approach can really quickly become computationally very expensive. Another option is to add more convolutional layers, and you can certainly do that, but as the network grows, specifying each convolution layers individually becomes quite tedious. So imagine having to define each layer by hand for a 20, 30 or 40 layer network. It's quite impractical. And this is where VGG's key innovation came into play, grouping layers by blocks. And these blocks can be easily parameterized. It's of course a programming trick, but that way we can create really more organized modular architecture for networks. And this is, remember when this was really developed, there was still no PyTorch around. So this was actually done in Theano, and it was more complicated. But this introduction of modules really led to a persistent feature of the following network architectures. And this not only simplifies the design process, but also makes it easier to fine-tune the model for very specific learning tasks. And so here's more about the concept of VGG blocks, really a foundational component of deep learning systems. So one key question that had to be answered was whether to use fewer wide convolutions or more narrow ones. And recent comprehensive analysis from other papers at that time has shown that using more layers of narrow convolutions actually can outperform very few wide ones. Remember, Alex used a few wide ones, and now what came out is that a lot of narrow convolutions can actually outperform a few wide ones. And this has been a general trend in network design, actually. Having more layers of simpler functions is generally more powerful than fewer layers of more complex functions. So what does a VGG block consist of? It typically has several 3x3 convolutions. Like here, if you pad these by 1, it maintains the spatial dimensions from the input to the output layer. And at the end of each block, there's a max pooling layer of 2x2 with a stride of 2, effectively halving the resolution. Now, imagine stacking several of these blocks together and combining them with dense layers, much like in AlexNet. Doing this, you can really create an entire family of architectures, and this has been done. There has been the VGG16, VGG19, and all the varying number of these blocks. And the number in VGG just says how many blocks have been used and stacked up here. So if you take a step back and look at the overall progress in network architectures, it boils down to making them deeper and making them bigger and deeper. And if in the debate between deeper versus wider networks, it turns out that deep and narrow structures are generally better, which really has been shown with the VGG architecture. So this is the overview so far. Starting off with LearnNet was simple, with just 2 convolutions and pooling layers, 2 hidden dense layers. AlexNet has essentially took LearnNet, made it bigger and deeper, but it was not just the scaled up LearnNet version. It also introduced innovations like ReLU, dropout, and preprocessing techniques. And then came VGG, which took the concept bigger and deeper from AlexNet and ran with it. VGG introduced really the notion of repeated blocks and architecture style that was both elegant and really highly effective. So takeaway here is that as computational power has grown, so has the complexity and effectiveness of network architectures. And all of that wouldn't have been possible without the power of vector parallel processing, vector processors and GPUs. Now let's take a moment to delve into this chart here, which is quite interesting because it plots throughput against accuracy for various CNN architectures. And as you can see, the VGG family tends to be a lot slower when it comes to throughput compared to AlexNet. However, what it lacks in speed, it more than makes up for in terms of accuracy. And this really tells us that while VGG might require more computational resources, it generally provides superior performance. So if you're interested in further comparisons, you can check out the link at the bottom here, where you get a kind of direct link to each of these network architectures. So this is an example implementation for VGG. Again, we can derive here now from various base VGG blocks how our VGGs should actually look like, and then get an entire family of network architectures out of the basic definition. So another stepping stone was really the inception architecture, which was maybe another landmark in the history of CNNs. And this architecture was designed by researchers at Google. So the big tech companies at this point also realized what potential CNNs have and started to do their own research. And what makes inception unique is really that it's both deep and introduces the concept of parallel paths within the network for the first time. So unlike previous architectures that had a single path for data to flow through layers, inception really offers multiple pathways. The advantage of these parallel paths is really to capture different types of features more efficiently, and the architecture really combines the best of different types of convolutions and pooling layers to enhance its performance. So it's this really unique parallel structures that made inception a go-to architecture for many more complex tasks. Really the effectiveness comes from not having to decide what convolution and what kind of combination you have to use. The only thing an inception block needs to make sure is that the output is at a defined size. You see in a moment how this is done. So let's take a moment to recap what we've covered so far. On the left, we have explored LearnNet, which utilizes 5x5 convolutions. Then we moved on to AlexNet, which employs a mixture of 11x11, 3x3, and 5x5 convolutions. And following that, we discussed VGG, which really primarily focuses on using blocks and 1x1 convolutions and so on. And you might think this is quite all a mess, right? It becomes confusing to decide which type of convolution should be used for optimal performance. Should we use 1x1, 3x3, 5x5 convolutions, or maybe even only max pooling or not pooling? It's really hard to make a definitive choice. And it was the dilemma faced by Google researchers in what we might call deep learning Stone Age at the time, when all of these things were pretty new and nobody really knew how to optimize them, in which direction to go. So for instance, if you opt for 5x5 convolutions, you will end up with quite many parameters, leading to a lot of computational cost and possibly overfitting, even though it might be more expressive. On the other hand, if you go with 1x1 convolutions, you'll have a more controlled, memory efficient architecture, but it may not perform as well. So what's the solution to this convolutional conundrum? Well, that's where the inception architecture comes in, aiming to bring the best of all worlds. So what really was the groundbreaking solution to the convolutional dilemma we discussed earlier? Simply put, the idea was not to decide on one type of convolution over another. So this novel approach really gave birth to what we call now the inception network, named after the famous movie at the time with the concept of we need to go deeper. And that phrase really inspired the naming of the architecture of this network. So an inception block is essentially let's try everything. This is essentially let's try everything approach to this problem. It includes 1x1 convolutions, because why not? It also has a sequence of 1x1 convolutions followed by 3x3 convolutions. And for good measure, it adds 1x1 followed by 5x5. Even max pooling followed by 1x1 convolutions finds their way into the inception block. And the idea here is really to throw everything into the mix, and hopefully something will provide the optimal solution, and the other paths might just be ignored. The network will learn, okay, ignore this path, use a little bit of that path, and use a lot of that other path. On the left side here on the slide, you'll see a simpler version of the inception block, and on the right side, more complex version that also incorporates 1x1 convolutions. And it depends how you design them. The key idea of inception is really to make these parallel paths and learn which path to take. And the inception architecture is really a clever way to integrate these various types of convolutions to cover really all bases. Now you might be wondering, how do all these different types of convolutions really fit together in the inception block? Well, the key to making this work is using appropriate padding. For example, the 3x3 convolution use half padding by 1, and the 5x5 convolution use half padding by 2. This really ensures that the dimensions of the input and outputs aligns all the time and remain the same, so you can combine them back into one concatenated output. And once this is taken care of, you simply stack all of these layers together. So now you essentially have different channels within the architecture focused on different tasks. And one channel might excel at recognizing cats, while another might be better suited for identifying birds. And this diverse approach is what makes the inception block really so interesting and effective. You might still be asking, why is this specific combination of layers the right one? The answer is the researchers probably experimented with many variants, and this configuration yielded the best result here. So this is why they stuck with these sort of inception blocks. There are many different versions of inception with different blocks. And for our purposes today, let's just say the research is a result of trial and error. And that's really the essence of the inception network and the inception block, combining different types of convolutions in a single cohesive unit where all are processed in parallel and the parameters learn themselves if this path is relevant or not. So how does it look like channel numbers and so on? So the first inception block in the first version uses 64 channels for the 1x1 convolutions. And for the 3x3 convolutions, it uses 128 channels. And for the 5x5 convolutions, 32 channels are used primarily because 5x5 convolutions already come with a large number of parameters. So 25 times 32 in this case. When it comes to max pooling, a few other dimensions are included. The goal is really to have all these different parts sum up to 256 channels in the end. So a critical advantage of the inception architecture is efficiency. So the inception block is really designed to use a relatively low number of parameters and floating point operations without sacrificing a lot of performance. And this is really a key benefit. For example, if you need 256 output channels, using an inception block would require only 160,000 parameters and 128 megaflops. Contrast this with using exclusively 3x3 convolutions in all of the paths. Okay, if you use in all of the paths 3x3 convolutions, which would cost about 3 times as many parameters and flops. And if you were to use only 5x5 convolutions in as many paths as you have in your inception blocks, it would cost around 8 times more, making the inception block far more efficient with its combinations. So the underlying idea is really that if you can accomplish the same task with fewer parameters and operations, the network should perform better. And this efficiency is really what primarily motivated the design of the inception block. So why is the inception block simple in terms of computational requirements? Well, we'll have to delve into the algebra behind it, which really elegantly balances complexity and efficiently. So the inception architecture isn't just about throwing everything at the wall and see what sticks. It's also about doing so in a computationally efficient way. So if we delve a little bit into the mathematics behind the inception architecture, which explains its efficiency, we start by looking at a specific layer with a convolutional kernel size of k by k, for example. 3 by 3 or 5 by 5 or some, whatever you choose. So you can express this layer's computational cost as k2 times c in, so k squared times c in times c out, where c in and c out are really the number of input and output channels respectively. So we also have to consider the dimensions of the input image represented by by mh and mw for height and width, of course. And notice these are fixed, right? So this would need to move over a little bit. So this is also fixed. These two are fixed sizes, and so the total computational cost then becomes basically C in times mh times mw multiplied by a sum over the different paths, each with its own kind of kernel parameters. So by carefully allocating resources, varying the number of channels and kernel sizes, we can really optimize the network's performance. In other words, the inception block really allows for a judicious allocation of computational resources across different paths, offering a more efficient solution than using a single type of convolutions through the architecture. So the full structure behind the inception network is often represented in stages for easy understanding. And the diagram you see is from the D2L book, Dive into Deep Learning, which really provides an intuitive visualization and more detail about all of the architectures than I could ever cover in this lecture. The network is divided into 5 main stages. So if we start with stage 1 here at the bottom, it's fairly standard and similar to other convolutional networks. It begins with broad convolutions and pooling operations to ensure basic translation invariance and quickly reduce dimensionality. And the use of max pooling in this stage really effectively halves the resolution of the input. Stage 2 also focuses on capturing spatial correlations and ends with a pooling operation. Again, pretty standard. And now things get interesting here in stage 3, where we introduce these inception blocks where we don't choose anymore which path to go. And you'll find 2 inception blocks. So this is 2 after each other, stacked on top of each other, followed by max pooling again, which will again halve the resolution. And what's critical to note here is that as we reduce the resolution, we increase the number of channels really capturing higher order features from the input. And following this, we have a sequence of 5 more inception blocks here in this stage, where probably most of the interesting nonlinear computations take place. So the authors probably experimented here again with various configurations and found that this one performs best, and then subsequent versions and follow-ups like MERB and NET, more advanced methods like genetic algorithms have actually been used to automatically search for the most effective architectures and block combinations, provided that computational resources are not constrained, because something like this is pretty expensive. So if you focus on stages 1 and 2 of the inception architecture and compare them to AlexNet, in AlexNet, the first convolution is quite wide. In contrast, inception starts with 7 by 7, followed by 4 instances of 1 by 1 convolutions, and then 3 by 3 convolutions along with pooling. So as you can see, it's not vastly different from what AlexNet does in its initial stages. The key difference really here lies in the number of channels. While AlexNet results in a 12 by 12 feature map, Inception really retains a 28 by 28 feature map, allowing it to keep more of the original information. So in essence, the first two stages of Inception offer really more compact yet information-rich representation compared to AlexNet. And in stage 3 of Inception, here we see really a lot of activity and variation, even within the first and second block of this stage. For example, the first block utilizes 256 channels, while the second one jumps to 480 channels. And this stage also reduces the resolution of the feature maps, taking you from an initial 28 by 28 down to 14 by 14 grid. This kind of dynamic allocation between channels and blocks is one of really the reasons why Inception is effective. Another point to note is that there are different versions of this network. So these versions often really differ in terms of number and stages they include. The variations, such as computational resources or complexity of the data, really play a role here, what to choose. So this was Inception. It's a forward network architecture. And stage 4 and 5 are structurally basically quite similar to each other. Now, the evolution, you see here to some point, probably there are more versions by now. There are incremental changes to the architecture, which usually led to more and more fitting to specific benchmark tasks. So any of them probably work. It's not, it's at some point imports ideas from subsequent architecture we will talk about in a second. Now, let's go over these block details. Where are we in our accuracy versus throughput map? And this comes here again from this website. So where VGG family was living somewhere here with Inception, we are now coming close to a very good accuracy and also relatively good throughput, better than VGG with still quite good performance. So these base architectures, what we learn from them is really just that dense layers are computationally and memory intensive. We want to avoid them whenever possible. So real-world problems with big input tensors and many classes will prohibit a use of architectures like you've seen now. And again, one-by-one convolutions act like a multi-layer perceptron per pixel, which has been exploited in VGG and then also to some degree in Inception. And we need a while to understand what actually is going on here and there when we develop these things. So there's been a lot of directions and variability explored until really more understanding and insights can be generated that lead to better and other directions. And trial and error is an option. We optimize basically like grid search here, and a lot of that has been done with trial and error, but then also the trial and error approach has been automated like in a normal map. And a very interesting example of that process is a component of networks that intended to prevent overfitting a domain shift, and that's batch norm, which has been introduced around the time Inception was there. And then the batch norm was introduced actually because these networks became pretty large, and the gradient had to go from here a long way down to the back, and a lot could have happened to the gradient. And a key innovation aiming to address this challenge in deep networks was informed by a lot of insights about how mathematically things behave, and the idea is actually quite nice, but the motivation was probably a little bit off. So deep networks often struggle with convergence, making training both difficult and really time-consuming. And some solutions like deep supervision exist, where you spin off certain losses here at layers earlier than the very than the very last one, and they involve backpropagation from intermediate stages to help the network. However, this approach has really limitations, and people have been thinking about better ideas for a long time, and batch norm was developed to solve exactly that issue. And the intuition behind batch norm is really great. It is that during training, gradients flow from the top here to the bottom. And as a result, the last layer, here the last one, the last layer up here, starts to really adapt first to the loss, followed by the layers below and below, creating a cascade of adoptions through the network. However, this leads to a little bit of a problem. At the bottom layers, as the bottom layers really adopt, they change the features that are fed back up to the top layers. So you have adopted this, but this one defines the input to here, and then you change this, and then you change this, which defines the input to here. So each layer's learning destabilizes the next, causing really slow convergence, a slow convergence process that takes a long time for the layers to adopt properly. And batch norm tries to mitigate this issue by normalizing the features within each mini batch. So thereby stabilizing the training process and speeding up conversion. So really what we do is, so the idea is really to make minor corrections to the layers by adjusting their mean and variance during training. So all we want to do is, we don't want to fully fix these layers, but rather fine-tune them using an affine transformation that the model learns during training. So we can learn parameters that tells us how much we can normalize each of the layers to make them, to normalize them basically between them. So an affine transformation essentially means multiplication and addition operations. So what we do is really compute the mean and the variance represented by mu and sigma here. So we compute the mu and the variance for each of the batches. And the next step is then to renormalize each input feature by subtracting its mean and dividing it by the standard deviation. So this is a feature, subtract the mean, divide by the standard deviation of that batch, and then we don't stop here. We really introduce two new parameters, this gamma and the beta. So it's a little bit like a bias term and a multiplicative term, but it's all linear. And this we can learn. So these two we can learn. These two are defined by the data, but these we can learn across the normalization. And these are really used to scale and shift the normalized features. This process here, this is called batch normalization, since we do this across the batch here, but across the training here. I mean, you might be asking why exactly this works, or if the initial intuition behind the correction of the internal covariate shift is why really batch norm was created. It's debatable. So the efficiency of batch norm has been proven across really a lot of experiments. We can just assume that, or the assumption was that by correcting this, we will get rid of the covariates, and then everything will converge quicker, and don't need to adopt, or don't need to, the training doesn't destabilize when subsequent layers are updated during backpropagation. So the complete understanding of why it works so efficiently is probably still a topic of ongoing research, but so equations do this for the mini batch, but the idea is really to adjust the first and second moment separately from the rest of the network learning here. And so the normalization is not, the normalization has been debated, has been shown that it's also basically injecting noise as regularization, similar to dropout. So you would not probably have dropout and batch norm in the same network, since both do actually normalization, regularization, so noise, since this sigma and mu does not really represent your entire training data. It's just from that batch. And by learning this, you're just having a regularized noise component, how you change your data. So its original motivation was the reduction of covariate shift. And it's probably not correct, because this paper by Lipton is quite an interesting one. They revealed that batch norm may even worsen covariate shift in a strict sense, yet it still aids in model convergence. And it turns out that batch norm is effectively acting as regularization by introducing noise. And so let's think a little bit how this works. So if you calculate the mean and variance of a mini batch, let's say 64 observations, since you're working with a small sample, both the mean and the variance are subject to a lot of noise here. And you then normalize the features using these noisy statistics, introducing a random scale and shift. They are now becoming random scales and shift. You then normalize the features using these noisy statistics, and the random noise acts as a regularizing factor, of course, because the training gets harder, which is why you often don't really need additional regularization techniques like dropout when you're using batch norm. However, this property really makes batch norm sensitive to the size of the mini batch. If your mini batch is too large, you're not introducing enough noise for effective regularization. If it's too small, the noise level becomes counterproductive, so really affecting convergence. This mini batch size sensitivity becomes especially significant in multi-GPU settings, where batch sizes are quite often adjusted depending on what you have. And so what happens during that is really a problem. And so one question that came up a couple of times during the last years is what really happens during inference or test time. So you don't want this randomness when you're using the model for doing actual predictions. So what you do is you fix the gamma and beta parameters that the model has learned during training, and then instead of using the batch statistics during your inference step, you use a running average for the mean and variance to normalize the features, basically. So if you're working with a dense layer, a single normalization is applied to all the activations in that layer with batch norm. In the case of a convolutional layer, separate normalization is performed for each of the channels. And batch normalization really calculates a new mean and variance for every mini patch during the training phase, so it's quite noisy. And it's essential to set the train flag correctly here in your network to ensure really appropriate behavior. Otherwise, you would relearn this during inference, and that's probably not what you want. And this because batch normalization really acts differently during the training and the testing phase, so you have also memory of these parameters. Okay, let's talk about one of the most popular network architectures from the recent years, and something that shifted probably a little bit the paradigms in how to build network architecture, since this is probably the most commonly used backbone for any kind of classification task you're currently finding in applications and on GitHub. So let's talk about ResNet. This is the go-to architecture if you want a reliable off-the-shelf network. The initial motivation really behind ResNet was a little bit unconventional, really focusing on the idea of gradients not effectively propagating through many layers. Something batch norm tried to address with a good idea, but then turning out to be achieving something different than they initially wanted. ResNet really wanted to solve this problem of gradients not flowing efficiently through many layers. And when you add more layers to a network, you change its function class, basically. You're making it more versatile to do more things, but also different. So more layers means more parameters, granting us the power to model really more complex functions. However, as we add layers, our function classes do become more powerful, but also diverge from each other. So imagine trying to approximate a true function, represented here by that red dot. So there's a red dot somewhere here. Here's a red dot. Adding more layers might get you closer to this initially. So this new function space here is now closer a little bit to that. But after a certain point, you could just drift away. And this situation makes it really difficult to make engineering decisions about how many layers should be in your network. In an ideal world, like the theory is presented in statistical learning papers, your function classes would be neatly nested as you add layers, each one more powerful but similar to the last. So what you want probably is a new function class where the old function class is completely embedded. So they are nested inside each other. So that means you're staying where you are and you're just expanding the function class and getting closer to your true new function here. Well, unfortunately, deep networks don't always really work in this way. So how can we make it more like this ideal scenario where each new function class with each new layer contains entirely the previous function class? And the goal is we to have function classes that are both increasingly powerful and nested. And this way, as we continue to add layers, we keep moving closer to approximating the true function. But the problem with this is also that these classes may not be convex, and the aim is really to make them as nested as possible, which is kind of contradicting each other. ResNet achieves this through, I would say, genius trick insight here by just enforcing this embedding. So the ingenious innovation of ResNet really came from He et al. In 2015, and instead of parameterizing around a zero function f of x equals 0, ResNet, so one of these functions here, so if we parameterize around this, ResNet parameterizes around the identity function f of x equals x. And this shift is incredibly insightful because when all parameters are 0, adding the input to the output results in the simplest function, which is the identity function. So you can think of this approach as akin to, say, a Taylor series expansion, but for neural networks. Now, as you tune your parameters, you start to diverge from this identity function. The beauty is that you don't have to learn the identity function from scratch, reducing really unnecessary computational overhead. It implies also a different inductive bias and allows for the addition of new layers without disrupting the outputs of previous layers. I'm always adding here the output of previous layers. I can decide to ignore this completely or completely change everything here, but based on that, I always add this new function here to whatever comes here through this path. So ResNet doesn't precisely implement nested function classes. It comes remarkably close by adding these paths together. The approach is really encapsulated in what we call a ResNet block here, and the input is added to the output residual, and this simple change allows for deeper networks without the integration problem. And also this residual here, which we add here from, so this is the previous function outputs, could be identity, this could be the identity function, this could be entirely changing the output, doesn't really matter, but it's always added to the residuals from before, so we get to something that makes sure that our function space is contained, whatever was before here is contained into our new output. So the ResNet, the residual network architecture, really consists of multiple building blocks, and each building block usually contains, so they always actually contain, of course, activations, usually a rectified linear unit, and the innovation lies in adding the original input back here. In some cases, we might add a one-by-one convolution on this residual on the input before adding to the output, especially if we need to change the dimensionality of the input to match the output, then we would do something like this and add some one-by-one convolutions to change really the channel numbers. And this setup makes it easier for the network really to learn an identity mapping, essentially enabling the network to decide whenever or not to change a change is beneficial. So this might do completely nothing, but it allows it to, if you stack a lot of them, then the learning will decide how far changes will really go, and the rest of the parameters will just be ignored or identity map. So this won't be lost, it will just be mapped as an identity map. What we are discussing here is primarily the forward function, which defines how the network transforms really the input to the output. And in a typical block, you'll have something like, say, y equals batch norm, convolution, followed by a rectified linear unit, and then another batch norm. And if the block includes a shortcut connection, you'd add the original input back to the sequence, and after applying another convolution probably to X. And this makes the ResNet really seamless. You need to probably choose the dimensions of your convolutions carefully, which is a concept we already covered when discussing the inception architecture. But here we allow it to learn basically infinitely deep. And so if we talk how this is implemented, this is really, really straightforward to implement in PyTorch. Just have here the forward function with batch norm, activation, batch norm, convolution, activation, and with that we have our block basically, and can vary this block around. And there are of course many variations of what you can do and how you can do. They all have in common that they allow for a residual connection for the gradient to propagate back, and also for the forward function to keep the residual within this function space. So if this might not add any more, then it might just learn the identity function, or vice versa. It will learn to correct the other outputs and other changes from the other networks. So anyway, it kind of closely resembles what we have previously seen, but the primary building block here is the ResNet block, not the inception block, for example. And a typical ResNet module may include a block with downsampling. This usually employs a stride of 2, and follow this, several other standard ResNet blocks are really stacked on top. And downsampling in each module is commonly performed using a stride of 2. And to introduce complexity and nonlinearity in the network, one-by-one convolutions are really often employed within the network block. So this is actually quite common to have here one-by-one strided 2 convolution. And so this can be really, really effective. And if we look in how many layers you can do with something like that, so it scales really, really well. You can do all the way from 18 to way over 200 layers. And the lower layers of this architecture really closely resemble what we have observed in previous architectures. It's basically VGG or GoogleNet or things like that. And they usually start off with a typical sequence of convolutions, batch normalization, pooling layers, and so on. And residual connections are a defining feature that contribute to the network's expressiveness. So this is really key here, and allow for quite deep but models without facing vanishing or exploding gradients or the change problem when updating the network. And to manage dimensionality, ResNet uses pooling and strides, just like early architectures. Batch normalization layers are the batch normalization layers kind of control the capacity and stability of the training process here through likely regularization through random noise. Depends really on, it's very sensitive to what batch size you are able to put through this network. So what makes ResNet particularly remarkable is that it's designed to be trainable at scale. And the naming conventions for ResNet variants is also quite straightforward. Like in VGG, the number of layers correspond to the variant name. So ResNet 18 is an 18-layered architecture. Now, looking at the throughput versus accuracy chart again, where are we now? So the ResNet family is somewhere up here. And with that, welcome to the state of the art of deep learning.
Till I walk in. Don't stop, make it pop. DJ Gomez, make this up tonight. I'ma fight till we see the sunlight.
If you use a reasonable ResNet, from ResNet 50 to 100 to whatever, you'll probably get really good performance or the achievable performance given the data you have for classification tasks here. So you might be wondering, is there anything after ResNet? Yes, of course. It's a valid question. So given how pivotal ResNet has been in the field of computer vision, there can't be much beyond, but ResNet opened really the floodgates to a whole slew of architectures that were inspired or built upon each other's foundational ideas. And it's just the tip of the iceberg. I can show you a few variants if you look through Archive or Google Scholar and various variants, or look at what you find in PyTorch model zoos and so on. There are lots of variants, a lot of them built for very specific problems in mind, a lot of them also slightly outperforming ResNet on specific benchmark tasks. DenseNet, for example, it's very popular as well. It stands for Densely Connected Convolutional Networks, and as the name suggests, its defining feature is really dense connectivity. So each layer in a DenseNet is connected to every other layer in a feed-forward manner. So quite unlike traditional CNNs, where each layer is only connected to its immediate successor. So what you have is you're connected to everything before. And the key advantage of this dense connectivity is feature reuse. So each layer gets the feature maps from all the preceding layers, not just the last one, the preceding, the immediately preceding layer. So this feature reuse not only makes the network highly efficient, but also requires fewer parameters for high performance. So you get a network that's both computationally and memory efficient. The dense connections also help alleviate the vanishing gradient problem, which is often a challenge in very, very deep networks and also allows to skip certain parts, similar to the ResNet, right? So this also improves the gradient flow through the network, and optimization is slightly easier on the DenseNet than say, an inception architecture. And additionally, the architecture itself acts as a form of regularization, so we reduce the likelihood of overfitting even when the model is very large. One of the really big wins of DenseNet is its scalability, so you can easily adjust the number of layers and other hyperparameters to make it suitable for a variety of tasks and data sizes. It really only depends on the computational power you have at hand to optimize such overparameterized networks. Another nice idea was Squeeze and Excite. The SENet is based on the idea of attention. You'll hear a lot about attention later in the course here. So attention basically allows a model to focus on significant features within the data. So rather than indiscriminately treating all features equally. And think of this like spotting the essential parts in an otherwise quite noisy scene. So imagine, for example, you have various channels within an image you're analyzing. Let's call them cat and dog channel and dinosaur channel. And these channels really represent the features that the model is focusing on at any given time. Now here's the tricky part. To efficiently recognize a cat, for instance, you think you need to focus on the cat channel, but how can you actually do that before you know it is a cat? And that's a paradox. And SENet tries to solve this. So in traditional convolutional networks, information moves relatively slowly from layer to layer. this can mean that it takes several layers for information from one corner of an image to influence the other corner, right? So it's a locality. So that advantage we discussed earlier is now sometimes a disadvantage if it's about large-scale context. And SE nets really are smarter. Say you have a bowl of milk in one part of the image. The presence of this object might actually indicate there's likely to be a cat somewhere else. So SENet uses this kind of contextual information to influence its decisions. So how does SENet do it? Very simplified, the network just calculates a global descriptor for each channel. So you get out these sort of descriptors for all of the channels. And these descriptors go through a small neural network that outputs new descriptors. And these new descriptors are then used to scale or excite the original channels. So it goes back and then scales up the channels that are important here. So the bowl detector and the cat detector would probably excite each other, and the network would learn this and adjust the weighting factors for each of the channels accordingly. And this is computationally efficient as well and offers a more refined way to focus on what's really crucial in the image. In terms of performance, SENets are a big deal. They are among the top performing architectures in various model repositories. And the paradox of really needing to know what you are recognizing before you actually recognize is addressed here. And the solution is the attention mechanism. So it squeezes the information from all the channels into a global descriptor and then excites or reweights each channel based on this descriptor. So essentially, it uses global context to guide the focus on specific channels without needing to first identify what the object is. So in summary, there are things to explore. AutoML or MurboNet and so on, this was all kind of solving the issue of manually fine-tuning networks, exploring new architectures and so on. And this automates the process of finding the model architecture. So don't try to find a new model architecture nowadays if you don't have a really, really good idea. Just playing around empirically with changing kind of parameters will not lead you to a breakthrough. Hypernetworks are quite interesting. They are essentially networks that generates weights for another network. So a network that predicts a network architecture for network weights for specific tasks. And these networks offer a higher level of abstraction and can be particularly useful in complex tasks. There are also networks with memory features like Canova machine, which really enables more dynamic and contextual decision making. Just realize that none of these networks we have discussed so far has any sort of memory. It doesn't know anything it has seen already. It just makes a prediction every time it sees a sample as if it would be the first time it makes this prediction. Interestingly also, it seems that the introduction of fundamentally new architectures has really slowed down. So for instance, NeurIPS 2020 showed already that the focus had shifted more towards meta findings rather than really novel basic architectures. And keep an eye out for the second part of this course where we also delve into the concept of attention a little bit more. This is something that really is very important, especially in this large language model domains, generative models and so on, where attention really is playing the key factor for their success. So in overall summary, Inception is notable for its inhomogeneous mix of convolutions, really parallel paths. That has been a kind of nice step, but ResNet really introduced the idea of residual learning, which can be thought as a form of, say, Taylor expansion for neural networks. Certain parts can be just left out without really impairing the gradient flow through the network. It enables to train also very deep networks, and there are extensions like ResNext and so on, where the ResNet is using decomposing convolutions, really offering quite some extensions for efficiency and also accuracy, throughput as well of these architectures. And there are DenseNet, ShuffleNet, SENets and so on, which are all really, really important contributions to the field. But in essence, the landscape of CNN architectures is really vast and ever evolving. Each of them have their own set of advantages, and they are tailored for different types of tasks and data. So finding the right one for your problem probably will always start with a generic say right now, ResNet. One takeaway is probably deeper doesn't automatically equate to better, as shown in the VGG network, especially if the function space isn't probably regularized and it probably easily drifts off to somewhere else. And regularization techniques really can help in constraining the function space, so dropout, batch norm, and so on, thereby making the network generalize better really to unseen data. And ResNet has undeniably become the workhorse of deep learning, at least for the time being. We'll see where we are going. But if you think you've got a groundbreaking idea that could surpass ResNet, it might be worthwhile to check if similar concepts have already been published on, say, Archive and similar. And also be careful with benchmark overfitting. So if everything is tested always on the same benchmarks, then certain decisions will at some point decide how the network architecture will perform, and then only perform well for that one particular benchmark. So bias is a really, really big factor here. And it's important to note that while various modifications and improvements have been proposed, the effectiveness often comes down to how well you train the network and also for what specific purpose. So architecture is just one piece of the puzzle. Training regime and the problem you're tackling is also a very crucial part in this domain.